Okay, exciting times. We are venturing outside of the realm of just basic lines, and today we're going to be talking about equations of planes. Now, I'll say in R3, but I think that goes without saying, simply because we don't talk about planes in R2, because that would be the Cartesian plane, and it would be pretty boring because there'd be one of them. So, going to think about planes in R3. Now, what we want to think about, I want to do the same exercise that I began yesterday's lesson with, where we talked about what it was the minimum suite of information we could use to define a unique line in R2. I want to think about what is the minimum info to uniquely define a plane in R3. Okay, and this is an interesting task to think about. So, I would encourage, I'm sure a lot of you are just going to kind of blow on through and just wait and listen to what I have to say. I'd really encourage you to think about different ways, what would be sufficient information to define, to make a unique plane in R3. I'm going to walk it through, but I would encourage you to stop and think about it for a bit. So, all right, so one way, and there's going to be different ways we can do this, is if we had, imagine that you took, you can kind of put your hand out in front of you and do this. If you put out two fingers, if you just made like a V with your fingers, and if you think about a plane, imagine that you had a piece of cardboard, and you laid that piece of cardboard on your two fingertips. Those two fingertips would represent 2 points. Like we're just talking about the tip of your fingers, those would be points in R3. If you put the piece of cardboard on there, it's not stable. It would tip, it would fall, it would wobble back and forth. So 2 points in R3 is not sufficient to define a plane. It would define a line. We talked about that. And so then you can think, okay, well, maybe I need 3 points. And you're right, 3 points would do it, but we have to be very specific about those 3 points, because imagine that you took 3 points that were perfectly on the same line. Again, you could have 3 unique points, but what it would do would define a line, and so you could put your piece of cardboard on there again, and it still wouldn't have any stability. The cardboard would tip off. So one way that we can do it is 3 non-collinear points. So if we had 3 non-collinear points in R3, that would be sufficient information to uniquely define a plane. And an easy way to think about it, or an easy-ish way to think about it, is, if I took a piece of cardboard and I flopped it out there, would that level of information be sufficient to actually, define a unique position for that plane? And yeah, it is. So, the way that we draw planes in R2, well, in 2 space to represent planes in R3, is we just normally do like a parallelogram. Probably should have been in Smart Notebook, but I'm not. So there we go. So there is a point, or there's the plane. And so planes are usually, they're represented, we would say pi 1, and that just means, plane 1. So normally when we're in 3 space and we're doing anything with planes, if you see a pi, it probably is a naming convention as opposed to 3.14, blah, 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 blah. So if we took this and we said, all right, if I had a point here that was, whatever, I'll call that one A, and then grab, and, here's another point over here that's B, and then here's another point over here that's C. Those 3 points, if they were hovering there in 3 spaces, you could, conceivably lay a rigid sheet of cardboard or plastic or whatever, and it would uniquely balance it, and it would define a plane. So there's one way. One way is we could have 3 non-collinear points, right? Because if they were collinear, put one there, the sheet of cardboard could tip either way. We don't want that, so they have to be non-collinear. That's important. Number 2, what's the second way we could do it? Think about it. How about if we had 2 intersecting lines? So I'm going to draw my, my plane representation here again. not the best one, but whatever. So if I took and I had, here's one line, and grab another line. If we have two lines and they need to intersect, you might wonder why they need to intersect, but it should kind of make sense, two intersecting lines. So if I had, this is L1 and this guy over here is L2, and they actually intersect, you can imagine that, if I had these two bracers, like, or two pipes that, went through one another, I could set a tabletop on top of that, and it would only sit in one orientation. It wouldn't wobble, it wouldn't do anything. But, there you go. So two intersecting lines, that's another way we could do it. All right, there's a couple more ways that we can get a unique plane. How about if we had two parallel, and I'm going to say distinct lines. So if we had two parallel and distinct lines, right? So I'm going to draw my plane here again. Right, so if I had a line went like, I want a color there. A line that went like this, and then, do my best to make them parallel. There we go there. So there's two parallel lines. So you can imagine if they're two parallel lines, we could come along and we could orient a piece of cardboard on top of that as well, and it'd be good to go. So L1 and L2, and they are parallel or collinear, right? So that's another way we could do it. And then there's one final way we can do it. And another final way we can do it is we can define it with a line and a point where the point is not on the line. Right? That'd also be sufficient information, right? So if you think about it, we took a plane, if we took, any old line and then, laid the cardboard right on the line, it would tip either way on the line. But then if you put a point somewhere out in free space, the line or the piece of cardboard would roll around that line until such time as it encountered that point, and then it would stop rotating and you would have your line. Or your plane, excuse me, right? So call this guy L1. Here's L1, and then just a point over here and a point. And that would be sufficient. So those are, each of these represents the minimum amount of info that you could use to define a plane in R3, right? And those are the different ways we could do it. So we're going to go through, and this is, we're going to slow down here on planes for a bit. We're going to do a couple days on planes. And then we're going to work with them exhaustively, but we're going to spend a couple days on just kind of dealing with planes like this. We're going to have to be able to, if I gave you 3 points, how am I going to get the equation of a plane? If I gave you 2 intersecting lines, how am I going to get the equation of a plane? And so on and so forth. So those are the different ways. And so those are the minimum suites of information. Now, let's talk about the vector equations of a plane. Okay, so vector equations of a plane. So vector equation of a plane. So if we think about the vector equation of a plane, what we're going to have is we're going to say plane 1, and this is how we're going to define it. We're going to say that, any point on the plane, so x, y, z, so this represents, any / every point on the plane, right, is going to be equal to, and then we're going to say a P naught, right? And so this is going to be an anchor point, right? An anchor point can be, again, any unique point on the plane. Right? Now, same as last time, I'm lying to you. It's not really an anchor point. In theory, what it really is O, dang it, O P naught, right? That's what it really is. It's really a vector that goes from the origin out to that point because we can't add vectors to points. But again, I always contend it's an anchor point, right? And so then plus So we get out to the plane, right? So this gets us out and onto the plane. Now, so if I was like, oh, there's a point on my plane here, so maybe I'll do that, so we've got this point on this plane out here. Maybe I'll draw a new one, right? So we got our plane here. Here it is. And I say, all right, there is my P naught, or O P naught, gets out to it. There it is. Right, so there's my point that's on the plane. I can't wander any old direction. I have to be quite specific in the direction that I wander. I couldn't wander, upwards away from the plane or downwards through the plane. I have to be really, really careful, right? And so with that in mind, we're going to say plus S times A plus T times B, where A and B are direction vectors. And I should probably say direction vectors that are non-collinear. So direction vectors that are contained within the plane. So if you think back to one of the things that we did early on, we talked about spanning sets. And we said spanning sets, a set is a spanning set if you can get to every point in R2 with some linear combination of those two vectors. So as long as they were non-collinear in R2, that means that we could always get to some random point in R2. So here, the direction vectors, so long as they are not collinear, right? So if I had one direction vector that said, hey, you can go this way, that's fine. And then we had another direction vector that said, yo, man, you can also go this way. Well, that's not the nicest direction vector of all time. Let's fix that up a little bit. If we had those, then we would be good to go, and we could simply say, all right, we can follow either of those direction vectors. So this could be direction vector A, and this could be direction vector B. And it says, okay, we get out to the plane, P naught's on that plane, and as long as you follow any combination of A or B, you're still going to be on that plane. And because A and B are non-collinear, they form a spanning set of all of the points on this plane. Okay, so in this case, obviously, S and T have got to be members of the reals, and A and B are direction vectors. That's a bit of a doozy, right? So that's one way we can define a vector equation of a plane. And remember, similar to when we first did direction vectors of lines in R2, we're going to show you the different ways. So these are all considered a vector equation of a plane. And so then it's going to be here, we're going to say it could also be that we have X, Y, and Z is equal to, and then we would just say X naught, Y naught, Z naught, so there's our anchor point again, plus S times A1, A2, A3, where there's a direction vector, plus T times B1, B2, B3, and there's our second direction vector, right? So that represents the same thing, okay? So it's important to know that vector A and B form a spanning set of all points on the plane pi. Okay, so there we go. So A and B form a spanning set of all of the points on the plane pi. So those are different representations of the same plane, just written, same vector equation of a plane, just written a little bit differently. So that's a vector equation of a plane. Not the only type of equation for a plane. Let's also then look at the parametric equation for a plane. Parametric equations of a plane. Okay, and the parametric equations of a plane are going to be formed pretty much the same way that we did for parametric equations of a line in R3. we're just going to parameterize these things. We're going to break them up into their components. And so we're going to say, oh, well, we have x is equal to x naught plus SA1 plus TB1, right? There we go. And then we could say, all right, that means that y is going to be y naught plus SA2 plus TB2, and z is equal to z naught plus SA3 plus TB3, right? So there are the parametric equations of a plane. Not bad, not bad. There is one more equation of a plane, and I would like to actually get into it. I think let's just try and experiment with this one a little bit. Let's do a couple of examples of finding these things. Or do I want to? No, you know what? I think that I really actually want to jump into. I normally wouldn't do it in this order, but I think I'm going to today. I'm going to get into also the final. Now, if we think, if we did lines, we had a vector equation of a line, and then we had a parametric equation of a line, and then we had a symmetric equation of a line. So let's, and then don't write this down. So let's go in red because it's cautionary. If we thought about, I think, is that red? Doesn't look red to me, it looks black. Symmetric equation. Let's think about that one for a second. Symmetric equation, what we did is we took and we solved for the t, and we had like, oh, so x minus x naught over a1 is equal to t, and y minus y naught over a2 is equal to t. Well, here's the problem. Which parameter do we solve for? And then there's still parameters involved. So symmetric equation, nope, can't do it for a plane. Okay, so no symmetric equations for a plane. But I hinted, more than hinted, I said, we do, however, have the Cartesian equation of a plane. I'm just going to write it, and then we're going to talk about how we're going to get it. So the Cartesian equation of a plane is ax plus by plus cz plus d equals 0. Now, sometimes I go into the derivation of this. I don't think the derivation's all that important. What is important is understanding how to get it and how to use it and how to interpret it. As it turns out, if we think about a plane in well, only in R3, but so we've got a plane here in R3. And we have different ways that we can represent it. We can do it with an anchor point and two direction vectors. That's the first thing. And then the parametric equation is just a different representation of the same thing. What's interesting about a plane has a normal vector. So there's more than one, but there's an infinite number, but they're all collinear. There is some vector that when it impacts with this plane, it doesn't matter what orientation you look at it, it actually forms a right angle with the plane, right? So there are lots of lines that you can look at in a certain way and get it to be a right angle with the plane, but there's only one, and I'm going to use that loosely, there's only one that it doesn't matter what angle you look at the line and the plane, it is going to be right angles to it, right? So think about it in terms of if you have a pencil with a flat base on it, you can stand your pencil up on the desk, and it doesn't matter what orientation it is that you're looking at it, it is right angles to the desk in every direction. Whereas if you tip your pencil over to a 45-degree angle, well, one way you look at it, that pencil is making a 45-degree angle with the desk. On the other side, it's making a 135-degree angle with the desk. But if you're looking straight down from above, it actually does make a right angle with the desk in some certain ways. The normal vector is what we are all about for Cartesian equations. So this thing right here is the normal. So I'm going to write that is the normal vector to the plane. Now, it's not the only one, right? Anything that is collinear to this is also a normal vector to the plane. So if we had one that was much shorter, just there, that's also a normal vector of the plane. And in theory, one that drops down and goes underneath is also normal to the plane, right? So we can have another one that goes, and so it should really be dotted, but I don't have a dotting tool here, right? That one is also normal to the plane, but they are all collinear, okay? So all of those, so these are all, okay, these are all collinear, right? So, I think that was red. Let's go get red again. So, the red N might be, 6, 4, 10. And then the blue N, well, maybe the blue N, it's only, half as big. So maybe it's 3, 2, 5, right? Um, they are scalar multiples of each other. And then that mint green one there, that's like that one there, maybe it's the opposite direction and it's even shorter. That's about the same length. So maybe it's -3, -2, -5. Those are all scalar multiples of one another, meaning they are all collinear. They are all normal to this plane. Now, the normal vector to the plane is actually going to be A, B, and C. So this coefficient, this coefficient, this coefficient, when you put them together, they form the normal vector to the plane. So it is perpendicular to every line that resides on that plane. And then D is, it's sort of a, it's it's going to be a constant that is going to help define where that plane is. So imagine this alternatively. Now imagine that you have like a pole that's spiked into the ground somewhere. You could walk along with a piece of cardboard that fits over that pole, and you could slide that cardboard over the pole so that it's perpendicular to the pole. That pole is perpendicular whether you have the cardboard near the end of the pole, or if you keep on pushing it halfway down the pole, or if you push it all the way to the bottom of the pole. That plane is perpendicular to all of those things. What the D is going to do is kind of help to orient where that plane resides along that pole. Okay. But what's important is A, B, and C are part of the normal vector to the plane. And then the D is a constant, and we're going to talk shortly about how to get that constant. Okay, so those are the different forms of equations that we can use to represent planes, right? So there's a vector one that's very similar to a vector equation of a line. It's got an anchor point and a couple of direction vectors. And then the parametric version is, it's very, very similar again, right? We just take that, the vector form, and we break it down into its x components, its y components, its z components, and there's the parametric equation. And then there is the Cartesian equation, and it's a tougher one. It's new. We've not done much like this. But what's important to know is the coefficients A, B, and C form a normal vector to this plane. So let's look at an example. Okay, so here we go. So find the, let's do all of them. Vector, parametric, and Cartesian. I'm going to run out of space on this page, but we'll stop and make another one. So the vector, parametric, and Cartesian equations of the plane defined by, now remember, we had 4 different scenarios, right? We had 3 points, 2 intersecting lines, 2 parallel lines, or a line and a point. I could give you any one of those scenarios, and you have to think about how we could get to these equations. I'm going to go with the easiest one first. The easiest one, stop and think. What do you suppose the easiest one is? Take a guess. What do you think of? The easiest one by a pretty fair margin is going to be two intersecting lines, okay? So defined by the two lines, now I'm going to make this one super easy because I haven't pre-cooked it more than anything else. If we had the line L1, which was going to be XYZ, is equal to 2, 4, -7 plus t times 3, 1, 4. And L2 is going to be x, y, and then z. X, y, z is going to be equal to 2, 4, -7 plus t times 1, -5, 3. Okay, so how do we know these are intersecting lines? Hopefully you can spot that pretty quickly. I can tell these are intersecting lines because this point and this point are the same point. So that means they must intersect. And I know they are not the same line because the direction vectors are not collinear to each other. So these must be two lines that intersect, right? Now, I could make this more challenging. I could have a different point here and they would still potentially intersect, but you wouldn't necessarily know that until you did some testing, right? This is a really huge unit that we're not going to get everything in, but I'm going to try and explain stuff as we go. So we want to find, let's first find the vector equation of the plane. Well, that one's going to be pretty easy. So I know that generally speaking, it's x, y, z is equal to x naught, y naught, z naught plus a times, or what do we do up top? I always change it around. S, okay, plus s times direction vector 1 plus t times direction vector 2, where s and t are members of the reals. So we need to find this. Well, this is pretty darn easy, and hopefully you can do this without me leading you, but if you need me to, that's fine. This needs to be an anchor point. Huzzah, there's an anchor point. 2, 4, -7. Plus, and we need two direction vectors. Well, look what we've got. There's a direction vector, there's a direction vector. They define the plane. So it would be plus s times 3, 1, 4 plus t times 1, -5, and 3. Lovely. There it is. There is the vector equation of the line. Huzzah. How about we get our parametric equations? Well, it's going to be x is equal to 2 plus 3s plus, I'm going to actually say it, 1t, and y is equal to 4 comma 1, or not comma, excuse me, plus 1s minus 5t. And then we're going to have z is equal to -7 plus 4s plus 3t. Okay, so there is the parametric form. Easy peasy. Now, the normal form, or the Cartesian form, excuse me. It's a little bit more challenging. So if we think, I want more space, so I'm going to save this one. So forgive me, guys, for taking a bit of time. So file, save as, and we're going to call this vector equation of planes. All right, save that, and then file, new. Okay. Oh, shoot. I don't have that now. Dang it. Hang on, let me open that up. Because I need that equation. All right, so, oh, I can make it bigger. Bigger. All right. So 2, 4, -7, and the vectors are 3, 1, 4. So 3, 1, 4, and 1, -5, 3. 3, 1, 4, 3, 1, 4, 1, -5, 3. So the vectors we have are 3, 1, 4, and then what was it? 1, -5, and 3. Those are the two direction vectors. So we had direction vector 1 was this, and direction vector 2 was that. I just want to confirm that that's what it was. 1, -5, 3. No, not that. This. 1, negative. Okay, there we go. Okay, so I have my direction vectors. And then what was the point? I need the point 2. And the point was 2, 4, negative 7. So 2, 4, negative 7. Okay, so Cartesian. Cartesian requires that it's ax plus by plus cz plus d equals 0. And we know that the normal vector is equal to a, b, c. Okay, so there's my normal vector. Now, the normal vector is perpendicular to absolutely everything on the plane. Every line that exists on that plane, the normal vector has to be perpendicular to it. So it needs to be perpendicular to this direction vector, and it needs to be perpendicular to this direction vector. So I need something that is perpendicular to both of those vectors. Hopefully the odd light bulb is going off in your head right now. How do we find something that is perpendicular to both of those? Well, you might say we could make a vector so that, maybe call the vector n, so that n dot d1 is equal to 0 and n dot d2 is equal to 0, because we know that dot products have to be 0 for things that are perpendicular, and then you could solve the equations. And you actually could do that. And in class, it's a pretty tedious task that I often assign for you to do it like that. However, hopefully you remember that the definition of cross product is it is perpendicular to both of its constituent pieces. So the normal vector is going to be equal to the cross product of our direction vectors. So I'm going to cross vector d1 with vector d2, and the result of that is going to be my normal vector. So let's go ahead and do that. So 3, 1, 4, 3, 1, 4, and 1, negative 5, 3, and 1, negative 5, 3. You don't get to play, you don't get to play, and then we have to do downy minus uppy. So we're going to have 3 minus negative 20, so plus 20. So I'll actually write it out. So 3 plus 20 is 23. So the x component is 23. And then we're going to downy 4 minus 9. So the next one is going to be 4 minus 9, which is negative 5. And then negative 15 minus 1. So that's negative 16. So I think that the normal vector here is 23, negative 5, and negative 16. And to confirm that you've in fact done it correctly, it's a really good idea to grab one of the vectors that you crossed and do a really quick dot product just to demonstrate that it's equal to 0 so that you know it's perpendicular. So I'm going to do that. So I'm going to say n dotted with D1, and I'm going to find out what that is. So it's going to be, I guess that's going to be 69 minus 5 minus 64, which is 0. So yay, I've done it correctly, right? So I feel good about that. So this is in fact the normal vector. Okay, so we're a little bit further along the lines. We know that the normal vector is A, B, and C. Now, if this wasn't in lowest terms, now would be the time to put it into lowest terms. Or if it had a negative leading coefficient, you'd multiply through by negative 1 to make it a positive leading coefficient. 23 is a prime number and it's positive, so I know that this can't be reduced, so I'm in good shape. So that means that this particular plane is going to look like 23x minus 5y minus 16z plus d equals 0. So it has to look like this. This is what this plane has to look like. But I'm going to have to solve for d. Okay. Now, I indicated that d is sort of the thing that tells you how far along that light pole your plane is, and it's moved up and down. Here's how we actually calculate it. You take any point on the plane. So normally we'd use our anchor point, and you substitute in the x, y, and z values, and then you solve for d. So this is going to be 23 times 2 minus 5 times 4 minus 16 times negative 7 plus d equals 0. So it's going to be 46 minus 20 plus 70 and 42 plus 112 plus D equals 0. Goodness, I'm going to have to get a calculator here. I think maybe so. That's 26, so that's 138. So I think D equals negative 138. Now, I might have made a mistake along the way. However, the general rule then is going to be 23x minus 5y minus 16z minus 138 equals 0. And that, ladies, gentlemen, and Jad, is the equation of that plane. Okay, heavy duty. So I'm gonna kind of take and write like a little bit of a cookbook recipe. We're gonna practice more of these, but the general recipe is to find the Cartesian equation of a plane. Okay, so we're going to use two direction vectors and cross product them to determine a normal vector. 2, the normal vector forms the A, B, C coefficients of AX plus BY plus CZ plus D equals 0. So now we've got a number here and a number here and a number here. And then the third step is substitute any point on the plane into X, Y, Z and solve for D. And then you now have A, B, C, and D. So you have AX plus BY plus CZ plus D equals 0. And there you go. That is how we find the Cartesian equation of a plane in R3. Now, what's special about this equation is every point on the plane satisfies this equation, right? So every point on the plane satisfies this equation, right? So that means that, if I have, if I say, oh, is this point on the plane? And, maybe the plane equation I gave you was not the Cartesian equation. In theory, you could substitute in and you could solve a big system of equations. The easiest thing to do is going to be convert it to Cartesian form like this, and then just do a left side and right side check and make sure that the left side and the right side both end up equaling 0. And then you know that the point is on the plane. And if it comes out to be like -1 equals 0, you're like, nope, this point is not on the plane, right? So there we go. So I'm going to do one more example here. Actually, maybe I'll write out a couple of examples and I'll leave them for you to do as homework because I have no idea how long I've been yammering, but I suspect it's a long time. All right, so I'm going to give you 2 more examples. And I'll work them out and include them in this note, or I will save it as a separate note. Regardless, I'll provide you with the solutions. So another example, how about a plane is defined by, and then how about, I'll give you 3 points. Imagine that we said point A is going to be 1, 2, 5. Point B is -2, 3, 0, and point C is 4, 1, 1. Okay, so a plane is defined by those 3 points. Now here's hoping they're not collinear. I can't imagine that I got so unlucky that they'd be collinear. They're not going to be. So I'd like you to find, determine all three, I was going to do three like that, forms of the equation of this plane. And how much room do I have? A little bit. Okay. And then a second equation or a second problem for you to try is going to be a plane is defined by, how about if we did two vector equations? So how about we had line 1 is going to be equal to 4, 7, 1 plus t times 1, 0, 3. And line 2 is going to be equal to 1, 5, 8 plus t times 1, 0, 3. So we can see that these are two parallel lines, and that was another example that we said could potentially uniquely define a plane. And so same thing, I want, find all three forms of the equation of that plane. Okay, there you go. Have a lovely evening, ladies and gentlemen, and I will post the solutions to this as well.